We're here at the Air Resources Laboratory's Atmospheric Turbulence and Diffusion Division in Oak Ridge, Tennessee. Dr. Bruce Baker is the director, and he will tell us about ATDD's research.
Welcome. ATDD was originally created to develop diffusion models to track the dispersion of accidental releases of contaminants. This research led to participating in scientific campaigns that examined atmospheric flows in complex terrain in urban areas and transport and exchange of nitrogen, sulfur, and mercury compounds. ATDD is still heavily involved in urban meteorology research and how land surface interactions affect the atmosphere and air chemistry. We are also heavily invested in NOAA's climate observing systems, which includes designing, testing, installing, and maintaining stations in all 50 states.
Bruce mentioned that ATDD studies the effects of pollutants like nitrogen and mercury on the air quality of the lowest part of the atmosphere, where people live and breathe, and also in remote places like the Arctic and Antarctic.
The atmosphere doesn't have boundaries or borders, so it's a shared resource for everyone. Part of our research deals with understanding how pollutants travel in the air so that we can maintain healthy ecosystems in communities. We study ammonia gas that's emitted from agricultural activities like fertilizing crops and raising livestock. We measure how ammonia is emitted, how it travels through the air, and how it's transferred from the air back to the surface. Our air quality research helps limit the harmful effects of pollutants in the air and in ecosystems.
I've been privileged to work in some of the most remote regions on Earth to advance our understanding of the global dynamics of mercury pollution. We are measuring halogen chemistry in Antarctica and Greenland and have learned that these halogens, recycled in the snow surface, are primarily responsible for the oxidation and deposition of mercury from long-range transport into these polar environments. Over the ice sheets, deposited mercury is sequestered in glacial ice, but over the marine environment, it accumulates in the biota, causing physical and behavioral changes in top predators such as polar bears.
And of course, we must examine the impacts of weather patterns on urban areas, our cities and coastal regions, where the largest populations are concentrated.
The DCNet Urban Meteorology Program addresses the issue of weather within the lowest layers of the atmosphere. ATDD's focus is on how the urban environment controls transport and dispersion of any possible airborne releases of hazardous materials. While our emphasis has been on providing first responders with timely assessments and forecasts, the DCNet weather stations deployed within the National Capital Region serve as the prototype urban test bed, providing weather data for applications ranging from homeland security to public health issues.
Fixed weather stations tell only part of the story. To get a complete picture, ATDD uses airborne platforms to compare meteorology aloft with ground-based measurements.
We have a long history using aircraft to make scientific measurements. A collaboration with Harvard University aims to measure fluxes of CO2 and methane from an aircraft over the North Slope of Alaska and Siberia in the summers of 2011 through 2013. Turbulence will be measured using our BAT probe, which was tested in the Wright Brothers wind tunnel at MIT. This test allowed the probe to be calibrated under flight conditions. Another study, in cooperation with the University of Tennessee Space Institute, measures the spatial variability of surface temperature around NOAA's climate observing stations. An aircraft has been instrumented to carry an infrared temperature sensor and other spectral instruments to measure incoming and reflected solar radiation. Test flights have been performed over climate observing stations in both Oak Ridge and Crossville, Tennessee.
Some airborne measurements don't need all the capabilities that an airplane offers. In those cases, we use balloons. This 3-ounce package transmits temperature, humidity, and location by radio to a computer on the ground. We use this information to study the planetary boundary layer, the layer of air in which we all live. Mixing one of the oldest forms of flight with the latest electronics technology, from the surface to 80,000 feet at 1,000 feet per minute.
To fully understand the Earth's climate, we must measure the energy exchange between the atmosphere and the Earth's surface and study the long-term trends in temperature and precipitation.
Our laboratory has a reputation for taking high-quality research observations. This is one of the reasons why ATDD plays an important role in NOAA's monitoring of climate. Observations from the Climate Reference Network tell us with confidence how much the climate of the U.S. is changing. Data from the Surface Energy Budget Network helps explain in part why the regional climates are changing. Understanding these processes and feedbacks are important for predicting future climate and are crucial for managing our freshwater resources. The locations of these sites and these networks were meticulously chosen to be in areas that would accurately represent the area. All of our centers are calibrated against NIST traceable standards, and the primary measurements have triple redundancy in order to assure confidence and completeness of the data record. Careful design and planning of the measurement systems have yielded data recovery rates that exceed 99%.
A constant challenge with our research is getting the best measurement possible. A reliable, accurate measurement assures scientific integrity.
Sonic anemometers measure wind speed and are used to research the exchange of energy and greenhouse gases between the Earth's surface and the atmosphere. This experiment has helped us understand wind speed measurement errors. We also study precipitation gauges. Air moving past a gauge is deflected, causing large measurement errors in snowy, windy conditions. We are evaluating different wind shields to help minimize this problem.
Often, industry comes to us for scientific expertise to improve their efficiency. For example, in the area of green energy, we've signed a research and development agreement with Duke Energy to improve short-term forecasts of wind fields where wind turbines operate.
There are still significant challenges in making these forecasts for specific or localized areas, and because the amount of power that is produced is very sensitive to the amount of wind available, accurate forecasts are essential in improving the cost efficiency of the power production. In short, this research could prove critical in further optimizing wind energy production for our nation.
We've explored ATDD's research and how it affects people, animals, and plants. So what do we do with our knowledge? How do we put our research to practical use? We share it with industry, communities, public officials, other scientists, and environmentalists to enable them to make informed decisions that benefit the Earth and her peoples.
Thank you. All right, that's good. Yeah. Thank you. Thank you.